Hi everyone, so I'm Jannis from TU Berlin. I'm going to present advances. It's somewhat also of an introduction to continuous diffusion language models. So this is based on joint work with Gregor Kornert and my supervisor Gabriele Steidl. And I'm very happy that the previous talk basically introduced many of the stuff I was hoping it would. So let's see, another warning. I'm a mathematician, so I cannot avoid all of the math. So as we saw before, okay, we have these two ways to generate a sequence which are being looked at a lot right now. We have this autoregressive approach and diffusion approach. And right now we saw this discrete diffusion. Here we have it again, a mass diffusion process. And in general, people know diffusion a lot more from continuous diffusion, right? Where for images and video, it's been the dominant approach in generative modeling to use some form of diffusion or flow. While in the land of language, so to say, autoregressive has been dominating, and recently discrete diffusion has become quite promising. On the other hand, continuous diffusion for language had a small peak in around 2022 or something, where it had some interest, and then basically people forgot about it. And until this year. So we're very happy about this. This year has been great for continuous diffusion. And we can see this here. So this is a little bit of a chart crime on my side, yeah. So 2026, it's not just continuous diffusion papers, but there are a lot more continuous diffusion papers this year. And you see, we had this peak in 2022. A lot of the stuff I'm going to be talking about, a lot of the ideas were already presented in this work CDCD by Dielemann et al. from DeepMind. And then we had this basically no continuous diffusion papers at all until 2026, and it's been going crazy a little bit, yeah, one after the other. So let's compare these two approaches on a high level, right? We just saw discrete diffusion, so I just leave this out. On the other hand, if we look at continuous diffusion, the idea is we want to work in a continuous space, right? We want to work in a space where we have a notion of what is close and not close. In token space, I don't know which word is closer to another one per se, but if I put these tokens into a vector space, then I can have some idea of closeness. And in this continuous space, we want to define some noising process, which starts somehow in our tokens, in our sentences, and goes to some noise distribution, and then we're going to reverse this process. Now, I visualized here 3 forward processes. First one is the mask diffusion. The second is uniform diffusion, which basically just says, okay, jump with a certain probability to a random token, just some other token. And finally, I visualize our own continuous diffusion process. Yeah, so there's something behind this. I'm decoding something from a continuous space, and you see the tokens here, okay? And what I want you to look at is the coloring. Yeah, the coloring here means if it's really green, the token that is there right now is very semantically similar to the one which was originally there in the sentence. Okay, so now we can run this forward process, and you can see the uniform diffusion with some probability they jump to something else, right? Now we look at the continuous case. I hope you can see Germany goes to Slovak, for example, right? There's a gradient in the coloring. This means our noising process is gradually going from tokens which are in some sense semantically similar to stuff which is completely random. And I think this is a really cool thing about continuous diffusion and this kind of like coarse-to-fine structure and stuff we were talking about before in the questions, is this idea that we can have a noising process even for language which respects some sort of closeness in some sense. So a quick roadmap, what we're going to do. First, I'm going to give a short introduction into flow-based generative modeling. So I have to say here, we use flows and diffusions like interchangeably, but in general we mean flows, and so we do the core idea how to do this in general, and then we're going to look at how do we do this for discrete data, right? How do we get the language in there? Now we're going to look at some design and training choices which I want to highlight, some most important ones, and then I'm going to showcase a little bit of our approach, so these what we did this year basically, and look at some of our experiments and some outlook where we think the field is going. All right, so flow-based generative modeling. I think many people have seen this idea. The idea is pretty simple. You have some simple source distribution you can sample from, P0, and you want to create samples from some target distribution, P1. Most of the time you have samples from this P1, and you can sample from P0. And now you want to learn some transformation that starts in P0 and goes to P1. And in this case, you can think about P0 being some Gaussian or something, and the idea is you sample from the Gaussian, you do your learned transformation, and now you have a sample from your data distribution. All right, how do we do this? Well, the idea behind flows and diffusions is, okay, let's define a path, right, between P0 and P1, which we call PT, some curve of densities. And we want a so-called velocity field associated to this path. Now, this is a little bit of math, but if these two together satisfy the so-called continuity equation, you can show that this velocity field pushes your initial source distribution to your target distribution. And what you do then to sample is you sample from your simple distribution, you take your velocity field that you get somehow, you solve an ODE, which is basically just saying, okay, I'm at a certain point, the velocity wants me to walk this way, okay, I do this, small steps repeatedly, and I arrive at my target distribution and should have some sample. Now the problem most of the time is the velocity field, P0 is simple, but P1 is very complicated and we only have samples. We don't want to solve this PDE, right? So what do we do? Well, the idea is to condition. Yeah, the idea is to say, okay, we're gonna build these curves of densities on conditional curves of densities, where we say, we know we're gonna end up at this point x1. And I'm highlighting this here with the most simple example, this linear interpolation, right? So we take some Gaussian, x1 is our data, and now we just say, okay, we define this interpolation between the points, it's just a straight line, right? This gives us a conditional density, which we can write down, which we can sample from, and importantly, we know the conditional velocity. Yeah, so we know exactly what, and along this conditional density is the conditional velocity. Okay, and then the question is, okay, what do we do with this? Well, the idea is what we really need is then the average over all these conditional velocity fields, namely this probability weighted average, this integral you see here. So this is really the thing that we want. Now the question is, how do we get it? Well, the nice thing in continuous diffusion is you use this loss. You take a network, you parameterize it, you regress against the conditional velocities, and as a property of mean squared error minimization, you get that what comes out, the minimizer, is exactly the marginal velocity field. Okay, so this is perfect. It's a super simple algorithm. I sample x0, x1, I interpolate randomly. At that point, I look at where should I be going, I regress to that, I keep doing this, and this gives me a flow. And people use this in state-of-the-art diffusion models. Now the question is, how do we get language into this, right? So we need some continuous space for language, right? Text is discrete. So what do we do? Well, in general, we have this thing in continuous diffusion for images, where if we see it, this cat thing, right? We have this cause-defined structure. This is exactly the question before, right? It works super well because the forward process removes detail first and cause structure last. And the backward process then creates cause structure first and details last. This works super nice. But tokens don't have any cause version, and we don't have some canonical continuous space. We have many, many choices we can make. First, let me set up some notation. So we're going to work with some vocabulary. Vocabulary, you can think about stuff like that, like tokens, word snippets. We're interested in random variables y, which are basically sequences which consist of tokens. And we're interested in sampling from the target distribution p data, which is the distribution of this random variable y given some data, right? So you can think of some examples. For example, a Sudoku would be n being 10. You have 10 tokens with the empty field and sequence length 81, for example, right? And for language, then n is 50,000 and L is, depending what you train, something between 500 and 4,000. All right. Now the basic idea is super simple. right? We know how to do flows in continuous space. We just need to get the tokens in there. The idea is define an embedding map. We take a really simple one. You take a matrix. Each column is a vector associated to one token. You put all of them in there and you say, okay, I either fix them or learn them, but these are now the vectors associated to my tokens. Now I have continuous data, right? And what I do now is, okay, I take a whole sentence. Each position gets independently noised. We take whatever vector the token is originally in the sentence, we add independent noise, and with this, we get a whole sequence that we can noise in a continuous space. And now, naively, we could say we just do the same thing we did before, but we have to be a little bit careful. Namely, what I showed you before is this marginal velocity field is this average of the conditional velocity fields. But for the discrete case, you can replace the integral with a sum. It's a finite state space. We only have n many tokens, right? Now, this conditional velocity, we assume we know it. For the linear case, we have this form, right? The only unknown here is this pt. And that's really what this focuses on. This is the difference from continuous image case and this language case is that the object we're going to look at is this pt. Namely, this is the only thing we need. Once we have this pt, we can compute the velocity of this flow in continuous space. So we already saw this pt before in the talk before, right? This is the posterior. This is telling me I'm giving you a noisy point, a sequence that I noised. And now you tell me what's the likelihood of each of the tokens, right? Which is the most likely token that should be here. So this is a denoiser essentially. And this is what we need to learn now. Now the first question is, okay, we need to parameterize a network. We want to output a probability distribution. Okay, in some sense we need to parameterize it so that it outputs a probability distribution. So we take some transformer. This outputs per position vectors. It looks at the whole sequence, but it outputs per position vectors. And what people do normally is they use some softmax decoder. Now, you can already notice that in this decoder show up our WKs. These are our embeddings, which we use to even define the curve in continuous space, where the tokens live. But we also use them to define the decoder. So if something here in this dot product is close, right? So these things are close to each other, they have a higher probability, right? So this is the key point. In continuous diffusion, you suddenly have these embeddings playing two roles. They are not only used for the output to get the probabilities, but they are also used to even define the flow. And okay, we can also use this at some point. If we want to go back from continuous space to tokens, we can always use this kind of parameterization to get back. So we already know kind of what our decoder is going to be. Now, how do you actually learn the posterior? So I'm going to just outline the recipe. It's super simple. It's basically what we did in the mass diffusion case, but now we do this in continuous space. The loss is basically the same. What we do is you choose some conditional path you can sample from and where you have access to the conditional velocity. You draw samples from this path and you minimize cross entropy at these samples. This means you maximize the log likelihood of the true token given whatever noisy version you see. And you can show the minimizer is exactly the posterior you need to get the velocity, and then you can do all sorts of things. So it's a very simple recipe. It's just as simple as in the video case and audio case, image case. You just have a different loss. Instead of regressing velocities, you're maximizing log probabilities. Okay, how do you then sample? Well, you sample some noise in your embedding space, in your continuous space. You have trained the posterior, right? You know the conditional velocities. You compute your velocity field. You run the ODE, right? Use an Euler scheme or whatever. You run it until time 1, and then you decode. And this gives you tokens. Now, I'm going to focus on some more design and training choices, which are native to continuous diffusion. So there are a lot of choices you can make, right? You can decide first, where do I put these tokens? In what geometry do they live? I can put them in Euclidean space. I can put them in the simplex and define something there. Later we will put them on the sphere and work on the sphere. There's many choices. There's many more you can make. Then the question is, what kind of path do you choose, right? You have some source distribution. You have some target. You need to define a curve. How do you do that? How fast do you walk along this curve? Where are the interesting parts happening at this curve, right? And the other thing is what the network really sees and predicts, right? This was a basic outline, but you can do a lot more things. You can parameterize your output head differently. You can do many things. Importantly, what we're going to look at is self-conditioning, which is widely used in this context. So let's get into it. And first, we need to learn the schedule once we do continuous diffusion. So we saw before we had this masking rate, right? And this masking rate tells us with what probability stuff will be masked. So it's either mask or information. So you know exactly in expectation how your information is being given to you, right? This is a discrete thing. I know something or nothing. In continuous diffusion, we are walking around in some token space. We don't know where the signal is. We don't know when it shows up. Yeah, a priori, I have no idea. So what do I do? Well, I just train the model. I look at the loss, and I see maybe, for everything after 1/2, the loss is already 0. That means it's trivial to read off the final token from the point that I am. But I don't want to spend half my time, if I sample T uniformly, training at trivial points, right? My model will be bad. So what we do is we need to learn the schedule. We can fit it to the actual curve, or there's many approaches to do this. And then what we do is we concentrate our sampling steps, both in training and inference, in this area there in the front. And this is the area where stuff happens, where uncertainty lives, where we need to decide where we need to go, and this kind of stuff, right? So this is a really important distinction between continuous and discrete diffusion. Discrete diffusion gets this for free. It's just 0 or 1. But here we need to be a little bit more careful and do some little bit careful engineering so that we actually train where the model learns. Second thing, self-conditioning. This was really interesting to me because I didn't really know why, and I still don't really know why this is the case. But apparently, if you feed the model the previous estimate that it just outputted, the previous posterior in some way, this really, really improves performance. So the idea is just you output some probabilities, you take this mean embedding, which encodes them, and you add it to your input. And now your network sees this. You have to be a little bit careful in training how you do this, so you turn it on and off with some given probability, but you do this, and what you see is for discrete diffusion, it makes a modest improvement, but for continuous diffusion, it's really a game changer, and you have to use it, basically. These are just like two general things you always need to do if you want to do continuous diffusion. I think this is also part of the reason it wasn't so popular, because it requires some engineering. You can't just start training this thing with like 10 lines of code. You need to put a little bit more effort into it. Now, I want to focus on a different design choice, namely the geometry and what we did there. And the basic idea is we want to flow on spheres. So the question is why, right? Like, why do we want to do this? Well, if you recall how we compute probabilities, you see we have this inner product with WK, and this WK serves two purposes. It defines our path and it defines our probabilities. Now, if we learn these jointly, which is what we do, if I leave them unconstrained in the norm, they will diverge and my training gets unstable. So what people do in practice is they normalize the WKs. They have to. And then this means the embeddings already live on the sphere. And now what we're saying is, okay, I want my flow to stay on the sphere. I know my targets are on the sphere. I keep my entire flow on the sphere. There are some other reasons, but this is the key motivation. Okay, then the next question would be, how do you do this on a sphere? I'm just going to tell you, like, I hope you believe me that all the stuff you can do in RD, basically, you can do on the sphere. With respect to flow matching, what we need are paths, right? That's the recipe. We need a conditional path and a conditional velocity. So the first choice you could use, for example, is, if anyone's familiar with this, is called slurp or the geodesic. It's just the shortest path. Take 2 points on the sphere, connect them via the shortest path. You get an interpolation. You can read off the velocity. Just do take the time derivative, and you have everything you need. What we propose is something a little bit different. We use the so-called von Mises-Fischer family of distributions. This is a density which only here depends on the angle between 2 points. This is an important part. And here it's visualized. If we have kappa being 0, it's a uniform distribution on the sphere. And for kappa going to infinity, it becomes delta. So it concentrates on this point W. I'm not going to go into too much detail why, but there are some reasons why we like this path. Now, for this path, one thing you can read off directly is you get the score, the conditional score in closed form, right? I can go back. Here you take a logarithm, take a gradient, project. So you get a conditional score. For those people familiar with diffusion, I hope you know what this means. But on the other hand, we have the conditional velocity. We need this. This was kind of like a big part of the mathematical work that we did, is deriving this. So you basically have to break down this continuity equation into a 1D equation, because everything just depends on the angle between points. You can do this, and then you can derive it as the solution of some ODE. It doesn't really matter that much, but basically we have access to this. We pre-compute some solution of an ODE, then we have a velocity field. And what you can then do is, okay, if I want the velocity field or the score, both are just basically some weighted sums with this posterior. I train the posterior the same way I always do it. So I can plug both in for anything that I want to do. Now let me overview just the whole thing, because I think there's a lot happening, right? So big overview of what we're doing. We take some tokens, right? We plug them in. Each position in the sentence gets its own sphere. So we're really working on the hypersphere. Then we again add noise, whatever path you want. We predict the posterior and use a cross-entropy loss. That's it. Rinse and repeat. That's what you do for training. And then how do you sample? Okay. I initialize with noise, random uniform noise. I compute my posterior. From this posterior, I can compute the velocity and or score. Once I have those, I just go in the direction of my velocity and repeat until time 1. And finally, I already have something that outputs the most likely token, right? So I use this to decode. Use my output head once more, and you take the argmax. So I start with noise on the sphere, I get out a sentence or something like this. This is the basic setup. Now this is a little bit more involved, but this is the basic reason we like the score. You can do these kind of things where you're doing a so-called ODE here with the velocity, and sometimes this accumulates errors. And so for those familiar with Langevin and predictor-corrector sampling, once you have the score, you can do these kind of predictor-corrector steps. Yeah, you don't go forward in time. You're basically adding a little bit of noise and then removing it again and hoping that this corrects some errors. And this is a little bit what our work focused on, and especially comparing what happens if we decide, like, okay, we do this many predictor, this many corrector steps, but we keep the total budget of steps fixed. So this is just for you to see. This is possible using this path. For example, for the other path with the shortest distances, you don't have a score, so you can't do this. So let me just show you some experiments and what these models do. So the setup is like this. What we did is, okay, we fixed the network and everything, how we do the schedule, all that stuff is fixed. The number of function evaluations are fixed, and we start varying the different paths. So we have our 2 paths on the sphere. We have this VP, which is just a linear interpolation I showed you in Euclidean space. Variance exploding is another diffusion path people use. And sometimes we also compare with the mass baseline, but often it's already in the literature, so we take those numbers. And then there's different tasks that we look at. For example, Sudoku Extreme is a extremely hard Sudoku data set, right? Now this is like the prime example people like to use in diffusion, because if you autoregressively solve a Sudoku, it gets pretty hard. And diffusion can do this much, much better, right? So you will find this in many, many, many diffusion for language papers, this Sudoku example. The other thing we look at is this called GSM-8K math reasoning. So these are grade school math problems where the LLM has to write code and then it's run. And if it's the correct answer, it's accurate, and if not, it's not. And finally, you have this very small text data set called like 1 billion words. This is like the smaller scale academic text data set that we run our models on. So firstly, let's look at Sudoku and what happens there. And I think we maybe start with the math baseline, right? You see it gets like 22% accuracy. And we were talking before about like revision, and I think you asked that like once a token is set, you cannot change it. And this is exactly the problem with mass diffusion. Once a token is set, without anything else, you cannot change it. So this performs pretty badly. Now, the nice thing about continuous diffusion is it never commits to tokens until the end, right? So you basically have this kind of like state which encodes a belief about what I think the answer is, which is developing over time. And until the end, at some point you have to decide at the end, but until the end you could, in theory, still change your mind. And you see this directly once we use continuous diffusion on this kind of Sudoku stuff. It gets much better. Of course, the VMF that we propose is the best. And we also see, okay, we use some predictor corrector sampling, and this works. Like the idea was we want to correct some steps. It does so, and we get even more accuracy. And I think the Sudoku dataset is actually really hard. Like, and there's been a lot of progress in like papers using masking and then adding some self-correction and stuff to get scores which are even close to this. On the other hand, we can look at language. So here's a generation of one of our models generating some LM1B sequence where the color indicates the confidence of the model. Yeah, even at the end, it's not really confident. It made some mistakes about some positions maybe, but you see how it develops during inference. Now, here's the thing. People measure how good a model is, or the community in continuous diffusion, using something called GenPPL, which is you basically produce samples and score them with a larger model. And at the same time, you also look at the entropy of your samples. This means how diverse my samples are. Now, this is the dominant methodology in the community. So I will say a little bit more about this later, but yeah. And what we see is our methods, which are all continuous here. I only included the best ones. This one is in Euclidean space. This one is on the sphere, especially with predictor corrector sampling, really performs well, at least in this metric. And we're not that far off of the discrete counterparts. We're even beating them, at least. Yeah, I will talk about the metrics, but at least in these metrics, we're really outperforming. Now, a caveat on the metrics. So this thing only looks at samples. It does not look at the distribution of samples, right? You're generating like 1,000 sentences, but each time you look at one and you score it and you look at the diversity, and then you basically average those scores. But it doesn't look at if the 1,000 sentences you produced are diverse between each other, for example. So this is a problem which I think the community is aware of. There was a paper like 1 or 2 weeks ago which really shows how you can hack these metrics. So all these numbers that I showed you are kind of like, they are definitely indicative of performance, but they are not conclusive. And we need some more metrics, and I'm also evaluating my models with better metrics now and stuff, but this is like, takes some time to get used to, and it's also hard to find metrics for this kind of stuff. So since we don't have the metrics, we like to go to this kind of GSM-8K thing, where the metric is really easy. It's just how good, how accurate are my answers, right? Are they correct or not? So this is a perfect metric. And what we see here is really our methods or maybe I start here, we have some other continuous and discrete methods. We see discrete around 18%. SFLM is another spherical method which came out like 4 days after us, which is able to, with some tricks, get to 18% or something. If we do nothing and just normally sample using the ODE, we get like this like 6-7%. But we can see if we use this predictor corrector scheme that we put in, we're able to get 31%, right? On the other hand, we see autoregressive at like 60. So there's still definitely a gap there, right? But we're getting better. So finally, a little bit of an outlook. So what really excites us about continuous diffusion is the fact that, so we've been working on diffusion for images and stuff for years, right? And there's so many stuff, so many tools you can use, so many papers, so many methods that are now unlocked basically for language if you're able to get good base models and stuff in as continuous diffusion models. So you can do this kind of few-step generation, which I'm going to highlight in the next slide. You can do guidance methods, right? If you want guided generation, there are many nice methods. And for reinforcement learning and reasoning model type stuff, there are also like a complete zoo of methods that have not been explored yet because basically nobody used continuous diffusion. So maybe one that I want to highlight, this year alone, we had 3 concurrent papers doing this. It's basically saying the idea is you have some flow. Normally you need to do many ODE steps to sample from it. Well, let's learn a teleportation, a shortcut basically. Let's learn how to jump from 0 to 0.25 and so on and so forth. This is called distillation or few-step generation. You learn a so-called flow map. You do this via some form of distillation, via something like a semigroup property for those who are familiar with this. And this basically leads to you being able to sample in very few steps. And that would really make diffusion contender versus AR stuff if we get this stuff to work really well at scale. So just one thing I would like to highlight. Basically, I want to summarize what we did is we built just in general continuous flow-based generative models and just basic idea of how to construct this. Then we embed tokens into continuous space. We look at how to train these models. And specifically, we looked at how to train these spherical models and how to set that up and what kind of results they get. And finally, a little bit of an outlook. I don't know, thank you for your attention. Open to questions.
Yes, so any questions for the speaker here? Okay, I see something like it.
Yeah, thank you for the nice talk. I have a maybe intuition question. So can you maybe give some intuition on why you would want your flow to be on the sphere? Like I get that you want the embeddings to be there, but like the shortest path in Euclidean terms would go through the interior, right? So why would this help?
Well, the thing is, okay, there's different parts of this, right? But so for me, some of the motivation was like saying, okay, I look at the softmax decoder and it decomposes into something like magnitude and direction, where magnitude controls basically the temperature, how confident I am, and direction controls which token I think it should be. Now, of course, I stick whatever the transformer outputs into there. But for me, it was like saying, okay, if I wouldn't even put a transformer between there and I just plug in the hidden state, I get, and then even you take this VMF path, I know you're a mathematician, so I can say this, you take this VMF path, and if you look at the unnormalized version and you normalize it, it's exactly softmax. So what happens is if you would sample from that and you compute the density, it's the same thing as computing softmax, and this kind of just intuitively fit to the whole setup. It's like, but basically, we want to remove confidence and we just keep whatever belief we think is. Like intuitively, the state encodes what I think the token is and not how confident I am I in this. This is still pretty hand-wavy, but yeah.
Thanks.
So for your token embedding, does it matter whether you use just some random embedding or if you use some pre-trained word2vec or whatever?
Well, there are a variety of choices. You can use some pre-trained embeddings, which also already have some clustering and stuff. If you use random embeddings, it's going to be bad because your cross-entropy head, it trains the model to put words like Germany and Slovak next to each other in your embedding space. If you just put random embeddings, it's much harder for your model to learn. What you saw in the original first slide, or not first, but here, right, is the fact that this happens, that they are semantically similar words I'm jumping to, is because I train this together, or I use pre-trained embeddings which already encode some form of semantic similarity. I personally train it in such a way that I train the embeddings jointly. And this works better for my models. There are other papers which do a little bit different stuff, which sometimes use fixed embeddings, but there's also a lot of engineering behind making that work.
Hey, thank you for a nice talk. Yeah, maybe another question. Didn't understand for the GSM 8K test bench there. What foundation are you comparing? Foundation models or just autoregressive models trained on?
These are all
only
trained from scratch at like fixed, I think, 100 million parameter models. These are trained from scratch on tiny GSM and evaluated on full GSM. So these are no large models that we are using for anything. These are from scratch.
Yeah, and the same for your diffusion model. And they've only seen this GSM 8K train set.
So all of the experiments that we do, we train from scratch, either on the L1B or on for tiny GSM, just on tiny GSM.
Thank you.
Yeah, thanks for the talk. I have a question regarding the training. So basically, the error comes from the classification, and then it propagates back to the denoiser, which trains your, let's say, velocity. And then you showed that with predictor corrector, you get better performance. So you are correcting for the marginals, right?
Yeah.
And I wonder if this hard bottleneck of discretization in the end, to turn it into classification, it's what making the model, the velocity field, inaccurate to train. And if basically taking a discrete approach from the beginning is better, like using discrete diffusion to say from the beginning on.
I'm not really sure, because what you're doing is in both cases predicting the posterior given some noisy state, right? So inherently, it's not clear to me why discrete diffusion would have an advantage there. They make the mistakes too. They cannot even correct them, because if you do mass diffusion, they lock into a token, right? So you can do some uniform diffusion and in theory correct it, but I think, and also experimentally, I don't see that discrete diffusion. I mean, I haven't trained these things at 8 billion scale, but I don't see this.
So I have multiple questions. First of all, you said a lot about like in comparison to the mass diffusion models, but also there you can like do remasking, and you can also do remasking based on the convergence of the probability distribution into the point vector. So I kind of don't get also like the continuous thing, and I really would want to understand it more. But the sample, like the output, you have like n tokens, so the output is also like n spheres basically, as I see it correctly now. And you also have like the same of like an n token sequence, and you can do the same syncing kind of process probably. But like, why would you say is this kind of thing better in the continuous way? Like, can you give maybe an intuition than like remasking strategies?
All right, so maybe I'll give you two different examples, right? First of all, remasking strategies mean you need to tack on a new loss. Many of the losses that you're doing, an extra training, maybe an extra network, are actually changing also like your target distribution that you sample, but you have to do this extra. This is not an inherent feature of your model, right? This is something you tag on after you've trained your mass diffusion model, let's say at a huge scale, and then you need to train another model for correction, right? You can train it jointly maybe, but this is an extra step. Well, it's inherent in continuous diffusion, this idea of self-correction. Also in uniform diffusion, for example, which is, I think, making also a comeback. The other question, what was it again? It was like
the thing is, like, for example, you also have like a logic like on the tokens, and you can say, okay, based on how strong the cross entropy in that vector is, you do remasking, so you also get it out of the model.
The other point is we can do the same thing, right? I can also look at my confidence. I can learn an extra model which starts pushing this around at certain positions. Remasking would then be renoising in some continuous space. I mean, this is not constraining me in any way, shape, or form if I'm doing this in a continuous space. Even I would say there was a paper that did discrete diffusion, and they built a noising process which they extra built it in a way to use it. It doesn't jump to random tokens, but to similar tokens. And you build this by using k nearest neighbor, basically on your GPT-2 embeddings, and you look at this, and then you say, oh, I have like 128, I take the closest one, and now I have a forward process which is like jumping to semantically close stuff. And I look at this and I say, I have it for free, right? I mean, super nice paper actually, but I was just like, in continuous diffusion, I have it for free. And I think this is just super nice. Another point about continuous and mass and discrete diffusion is we had this factorization problem, right? You sample from the mass thing and you don't know if you're sampling that token, the DAC token at the same time, like the New York stuff, right? This doesn't happen here because we only sample at the end, right? It's already converged to something. So I'm quite a fan of continuous diffusion, so...
So let's be correct. But so even if you pre-train, right, then you still have let's say boundaries between clusters, right, in which you can jump from one object to another, right? Like for example, like I guess dogs and cats will live more or less close to each other, right? So you can jump in a completely different category if your predictor makes some mistake, right?
Yes, I mean, I tested this, and very much so. They cluster, cat and dog are close, Germany and other countries. The idea of this kind of stuff happens. And this means just a small change can push you from cat to dog, like in some sense. But I think this is good. This is what you want, right?
I guess between countries, yes, it could be okay, but
I mean, if you look at
to dog is quite different. I don't know. Yeah.
If you look at GPT embeddings, they have the same thing.
Yeah.
No,
the problem is
they have the same
problem
thing.
is I'm saying it's still there. Yeah. Okay.
This is not a problem. This is a feature. Really, this is great.
Can I ask about scalability of such approach? Like, because I'm not sure if I understood correctly, but you trained on these super small models, right?
Yeah.
And if you would scale it to modern day LLMs, would you consider it inefficient regarding compute?
So it's comparable with discrete diffusion. The models I'm building are basically the same compute requirements as discrete diffusion models. If you use self-conditioning, this is a little bit, but even if you saw Diffusion Gamma, this new open source diffusion model from Google, also uses self-conditioning. So if we're on that same base, it's the same complexity as discrete diffusion. Same flops, etc. The scale, there are some papers scaling these models to around, I think, like 1.7, 2 billion parameters, which just came out. One from Apple, for example, that also did this floor map distillation. They show it's possible. I'm pretty sure you can scale them at least to this like LADA scale. We have to go to LADA scale and see, right? This 8 billion, this is basically somebody needs to train this and see how good it is.
Regarding inference,
yeah,
is it the same as for discrete, the amount of steps?
I mean, it's even if you distill, it's much less.
Much less.
Right?
Okay.
you can get much better performance in lower steps. If you don't distill, even then, I think, at least in my experiments, you can get matching or better than discrete diffusion. But again, right, this is at the price of some extra engineering and stuff, but once you figured it out, it's fine.
Okay. Good luck.
Thank you.